my name is Nako Nakatsuka. I'm a fourth year chemistry PhD student at UCLA, and today I'll be helping you guys out by going over some general chemistry concepts. And good luck with the course. So now here's a better picture of the piston diagram that I drew out really roughly for you before. And so if the piston moves out, like so, then the energy of the system has decreased by a certain amount, and this is given the form of work. And so work is force times distance. So the force is the amount of force that you're using to pull out the piston, and the distance is the amount that it moved. And since force can be written as pressure times area, right? The amount of pressure that you're putting into something and the area that you're lifting up, we can rewrite the work equation as pressure times area times distance. So now, if you have area times distance, you can write that as the change in the volume, right? The volume inside of the cylinder. So work can be written as pressure times the change in the volume. Okay. So now that's this dx right here, which is the change in the volume based on the movement of the piston. So when you move it up, based on the amount of pressure that you're using to do that and the change in the volume, you can calculate the amount of work that was done. So energy used as work of expansion is given the formula work is negative P delta V. And this is a very important equation, so make sure you know it. So let me write down what this represents. Energy used as work of expansion. So expansion is when you move it up and you're increasing the volume. P is the external pressure that the system has to push against. This is also occasionally written as P external. And we also want to check the units, right? So pressure is in the units of kilograms per meter second negative 2. And so since all of thermodynamics is the study of changes in energy for systems at equilibrium, we refer to all changes, such as the change in volume, as occurring in very small steps. So since we're looking at changes in energy for systems at equilibrium, changes occur in small steps. So we can rewrite this equation, and this is where a little bit of high school math comes into play, where work is equal to the negative sum of small increments of Pi delta Vi. If the system is at equilibrium, where the pressure that's internal inside of this container is equal to the external pressure, then the change in volume is infinitesimal. It's absolutely tiny. So the correct notation for such small changes is the derivative, or d. So delta Vi is actually dV, since it's such a small change when it's at an equilibrium. So when P internal is approximately equal to P external, delta Vi, or the change in the volume inside of this container, is going to be written as a derivative. To sum an infinite number of steps, we use the integral. So now work equals the negative integral V1 to V2, P external, dV. So now what this means is that we're taking the integral from a particular volume V1 to a particular volume V2, but since this change is so small, we're writing it out as the derivative, dV. Since the system is at an equilibrium, this is also a reversible process. And from now on, we refer to the system. So now let's talk about internal energy, which is given the sign U, and it's another state property. So remember we talked about enthalpy before, which was a state property, so is internal energy. And this represents the total energy from all the atoms and molecules contained within your system. So changes in internal energy are a function of the initial and final states, just like when we talked about enthalpy, since it's a state property. So delta U is going to equal U final minus U initial. What does this mean? Well, if delta U is positive, it means that the final U is greater than U initial. And on the other hand, if delta U is negative, then U initial is greater than U final. So in this case, we're looking at a closed system. And we know that the energy of a closed system can be changed by heating or cooling or by compression or expansion. We talked about this before. So we can change the energy of a closed system by heating or cooling. So an exchange of energy in the form of heat, right? Or by compression or expansion, which I showed in the work example. So if you look at this diagram, you can see that only heat is being exchanged with this closed system, whereas in an open system, matter can also be exchanged. So the change in the internal energy is the energy transferred by heating plus the energy transferred by compression, the combination of these two things. And so we can write this out as delta U is Q plus W, where this is the energy transferred in the form of heat, and this is the energy transferred via compression, and this is representative of work. So delta U is a state property or a state function, but heat and work are not state functions, they're path functions. So if the change in the volume is 0, or rather constant, then delta U equals QV. And remember, this small subscript means at constant volume. The reason for that is if there's no change in volume, there's no compression or no expansion, right? Remember that piston diagram? Like so. I'm going to draw this not so great diagram on the side again. There we go. And remember that compression is when you push it down, expansion is when you move it up. And so if the volume inside of this chamber is being held constant, then no work is being done on the system or by the system. And so the change in the internal energy of the system is entirely based off of heat. So for example, combustion in a sealed container where delta V is 0 and the change in the internal energy results from the heat released by the reaction is a prime example of when we would use this equation. So let me also circle this one because this is a very important equation to remember. So on the other hand, if the change in pressure is 0, so this is constant, then delta U is Q at constant pressure plus work. So in this case, if there's a change in pressure, if the pressure is held constant, remember that work can still be done on the system or by the system, but since we define the amount of heat released or absorbed at a constant pressure as the enthalpy, we can write QP as equal delta. So on the other hand, if pressure, or the change in the pressure, is being held constant, so delta P equals 0, in this case, delta U is written as Q at constant pressure plus work. So work is still going to play a part. But remember, we define the amount of heat released or absorbed at a constant pressure as the enthalpy. So remember this equation that we wrote before, delta H equals QP. So for a reaction occurring at constant P, we can rewrite this equation as delta U is delta H minus P delta V, where P delta V is representative of work. So this part came from work equals negative P delta V. So this is another really useful relationship where all we did was substitute in the terms for the heat at constant pressure and also the part for work. So for reactions at constant pressure that involve changes in the number of moles of gas, then P delta V is significant. So remember this equation that I just wrote out, delta H minus P delta V. If this is a gaseous system, P delta V is very significant because changing the pressure and the volume is really going to affect gases, right? But even for reactions with constant pressure that involve solids and liquids, on the other hand, this part is insignificant. So delta U is Q at constant pressure, which equals delta H, because the volume of the reactants equals the volume of the products. In the case of solids and liquids. And thus, this part, which represents work, is not significant for solids and liquids, but it is for gases. So now let's do an example. An exothermic reaction has a delta H value of negative 50 kilojoules. And this occurs in an open beaker producing 8 moles of gas at 25 degrees Celsius. And the question is, what is the change in internal energy of this system? So what is, delta U? And so we can make the assumption here that the pressure is 1 atmosphere, so standard state, and we can also use the gas law, PV equals nRT, to rearrange some equations. So first of all, let's write out the key equation. Delta U is Q at constant pressure plus work. And remember, we rewrote this as delta H minus P delta V. So we can find out this part of the equation by rearranging PV equals nRT. So let me show you that right here. P delta V is the change in the number of moles of gas multiplied by the gas constant and the temperature. So we have the change in the number of moles is 8 moles multiplied by the gas constant, which is just a value that's always given to you on exams, and you can also find it as at the back of your textbooks. and the temperature is given to us as 25 degrees Celsius, but due to the nature of the units of the gas constant, we're going to convert it to kelvins. So going from degrees Celsius to Kelvin, you add 273, and so it's going to be 298 Kelvin for 25 degrees Celsius. When you multiply this out, we're going to end up with units of joules, which is good, and we get 20 kilojoules. So then, delta U is delta H minus P delta V. We know what the value of delta H is. It's negative 50 kilojoules minus 20 kilojoules, which gives us negative 70 kilojoules. So a few things to remember here are always remember to cancel out the units so you know what you end up with. The answer that I would have gotten in this case would have been in joules, but I converted it to kilojoules by dividing by 1,000 in order to get it to the same units as the delta H value. Another thing is to review your gas law equations if you don't remember learning PV equals nRT. This is for ideal gases. And it's a very important equation that we use to convert different units into equations that we can actually solve. So as you can see, this has an internal energy change of negative 70 kilojoules. It's an exothermic reaction with a negative delta H value, and we could figure out how much that change was.